Hello class, this is the pre-class video for section 1.2. A lot of the content for 1.2 I've already touched on and gone deeper in the peanut butter book. So I'm going to go a little quick on the more straightforward, easy stuff so we can spend more time on the later stuff like projections, which I still have done a bit of that in the peanut butter book. So one thing that the book is not very good at, and sometimes mathematicians in general when they teach, is motivating new ideas. So this is a good example. Here's the dot product. They just throw the dot product out, say, hey, here's a dot product. And they don't say where it comes from at all. We just start off with the definition. Okay, if you have two vectors, we're going to define the dot product to be taking each of the corresponding values, multiplying them together, and then we're going to add up all of those pieces. So you end up just getting a number. Okay, you don't get a product out, you just get a number. There are different ways to define. So basically the question is, how do you define multiplication between two vectors? And there's actually different ways you can define a multiplication or a product. This is the one we're going to use the most. There is one later we'll bump into called the outer product. There is one called the cross product, which is very useful, but we won't cover it in this class. You'll see it in multivariable calculus for sure. So we're going to be focusing on the dot product. So one key thing is when you're working with vectors that you're multiplying, you need to be sure to specify which product. So on an exam, on your homework, whatever, be sure you're putting a dot in here to specify, hey, I'm talking about the dot product. Because if you just do this, like a u, v, that's not defined if these are both vectors. So this is ambiguous. We don't know what we mean by that. Okay. So here's some practice calculating. We'll just go through an example. So we've got a u and a v. How do you do the dot product? Well, 1 times a minus 2, 4 times 2, a minus 2 times 5. And if we can calculate each of those terms, you get a minus 2, 8, a minus 10. Add them together, you get a minus 4. So the dot product is minus 4. You can do the dot product of w and then u, and you'll get the same thing because the multiplication here for each of these terms is holy cow, I forgot the word. Not associative, commutative. There you go. Here are a few basic facts. This is the one they just kind of showed in the last slide. U dot v is equal to v dot u. It is it is distributive over addition. Okay, so it does have a distributive property. You can pull constants out, so it's associative with respect to constants. This notice we don't ever have something like this, where these are dot products. The reason is you could take two of these. So the question is like, well, is it associative? What if we have three vectors and we're dot product each of those? Could we do this and then dot that with w? Well, no. I mean, you could try u dot v, but that's going to end up being a number. And then you have a number dot w. And a number dot w doesn't make sense. To do a dot product, you have to have vectors of the same length. But this is a constant. And even if you did v dot w and said, okay, let's just let this, if we're going to do this side here, and we will just say, well, we don't want this to be a dot product. We want it to be a just the regular multiplication, a scalar multiplication. Same thing over here. You're not going to actually get the same thing in general, because here you're going to have a scaled version of W. Here you're going to have a scaled version of U, and if they're pointing in different directions, there's no way you can get the same thing. Well, unless your scale is 0. But, so this is one place where vectors start to break down from the arithmetic of real numbers. U dot U is always greater than or equal to 0, and it's U dot U is 0 if and only if U is 0, and I have the proof here. Basically, you're squaring each of the values of U, because this is the U dot itself, so you're squaring each of the values. So all of those have to be 0 or larger, and the only way that each of those terms could be 0 is if each of the entries is 0. So that's the way the proof goes. A note, this is a good section to start paying attention to proofs and how they're written and the logic, because you will be doing proofs in this class. This section is a good one to kind of introduce that, because the proofs, like as you go through the book, it'll do some proofs. And they're pretty easy and straightforward in terms of college proofs. They're very algebraic. They should have a pretty familiar feel to you, because a lot of it is manipulation by rules to show the proofs or properties. The length of the vector, notice this in here looks very similar to this term, this here, U dot itself. You just end up with each of those things squared, and so you can use this to find the vector. We're basically using the Pythagorean theorem here. The distance in each direction squared from beginning to end. Then you take the square root. So it's the length of the hypotenuse in an n-dimensional space. Like if this is the vector 4, 2, then, this is the vector 4, 2. Then the length of that, using the Pythagorean theorem, would be 4 squared plus 2 squared square root, and that's exactly what this gives you. Notice that this is new notation. This double absolute value. It's called the norm notation. This stands for the length of V, and this is the computation to get that out. It's all based on the Pythagorean theorem. The only way to get a length of 0 is if V is the 0 vector, so all of the entries are 0, however far down you go. And we do have this nice property. If you multiply a scale, a vector by c, then it just multiplies the length by c. See that here, if you double u, you're just going to go another 4 and another 2, and you can work out the math, and it'll end up being double the length. Makes sense that it should be double the length, and the calculation works out. So we can work through an example here in 3 dimensions. What's the norm of u, the vector u? Well, the norm, it's the square root of u dot u, and u dot u will get us 1 times 1, 4 times 4, a minus 2 times a minus 2. So that's a total of 1 plus 16 plus 4. So we get a total of 21, so it's the square root of 21. That's the length of this vector. And w, you can do the same thing with w. You should get the square root of 33 down here. We'd also like to normalize the vector. So normalize turns out to be really helpful to have vectors of length 1 in lots of applications and lots of the mathematics. It's nice to have length 1, vectors of length 1. So you can take any vector, divide it by its length, and you get a vector in that same direction, but it has a length 1. So u hat is the unit vector. So to calculate the unit vector, you take the vector u and you divide it by the length of u. And so here we're dividing by, this is dividing by the length of u, and this is u right there. So, okay, and similarly do that over here with w. We can go from length to distance. The idea is, if you have what's the distance between two vectors? If you start their tails at the same spot, then you look at the distance between where their heads are. So the ends of the arrows. So you can find the vector that goes from one to the other. Doesn't matter which way you go, that length will be the same. So you start their tails at the same spot. You find this new vector, u minus w, or you can do w minus u, and then you find the length of that. So that's what this is. This is the length of the vector that goes from the head of one to the head of the other with their tails at the same point. And then you can work out the math. 1 minus a negative 2 is 3. 4 minus 2 is 2. A minus 2 minus 5 is a minus 7. And the length of all that, you square each of these. So 9 to 49. That's going to get you 49 plus, 9, 4, 49. It's going to get you 49 plus 13, which is 62. So square root of 62. Okay, here's two inequalities. These are much more important inequalities if we're doing a proof-based class. We will do some proofs to help with your reasoning and understand the importance of some of the ideas and understand the connections. We won't be coming back to these as often, but they are something that you're expected to know. And for many of you, these will come up, especially the Cauchy-Schwarz inequality will come up in later classes. The Cauchy-Schwarz inequality is it's the harder one to explain and give geometric interpretations to. The triangle inequality is the more straightforward. In fact, there's a fun story about that. I'll tell you in a sec. But the Cauchy-Schwarz inequality says the absolute value, so this is the absolute value of the dot product of u and w. So u dot w is the dot product of u and w. It's just going to be a number, okay? So we don't need norms over here. It's just going to be a real number, so we can take absolute value to make that positive. The length of u and the length of w, those are always going to be positive. Well, 0 or positive. 0 or greater. So it says if we take the lengths of each of them and multiply them together, that's always going to be greater than or equal to the absolute value of the dot product of those two things. And again, this turns out to be important in trying to prove some of the properties later on. The triangle inequality, you can easily see here, u plus w. So here I have u, here I have w. So u up, w down. U plus w is the vector that goes from here to here. And the length of u plus w is always less than or equal to u and u plus w. So the distance around, the distance to go from here up and then down, is always longer than or equal to go here. If this is u and this is w, then u plus w is the same length, and then they could be equal. So if they're pointing the same direction, you can find places where it would be equal. Now the Greeks thought this was, they made fun of Euclid, a mathematician in many, many years ago, 300 years before Christ. They made fun of him because he worked really hard to prove this, and they said, this is so obvious even a donkey knows this. So let me draw my poor donkey here. Okay, they said if you put a donkey at one vertex of the triangle and you put food at the other end, then the donkey's going to go that way and not go around. So even to get to the food. So even a donkey knows this. It's so obvious. Okay, now we're getting into things that are a little bit more technical. I spent quite a bit of time in the peanut butter book building up to this. This is one of the key uses of the dot product and in kind of this vector calculus, this vector mathematics, is being able to use it to find angles. And the connection is if you have two unit vectors, so unit vectors meaning they have the length of 1. If you have two unit vectors, then the dot product of those unit vectors is the cosine of the angle between those. And so you can easily find the cosine of the angle, then you can take the arc cosine to find out what that angle actually is. So this is extremely powerful. In chapter 5 of the peanut butter book, I kind of walk through a bunch of like how these vector operations are very valuable in terms of just practical 3D geometry or higher dimensional geometry, and this is one key aspect of that. If you know coordinates of things, then you can find vectors to. You can find differences of coordinates to find vectors, and then you can use the dot product to find the angles. It's pretty slick. So here's an example. These are the vectors u and v from a few slides ago. U and v. So let's find the angle between those. So we're going to take u dot v. You can do this either way. You can find the unit vector first, and divide all these by the square root of 21. First, you can do that first and divide these by the square root of 33. It's a little bit easier to do the dot product first, usually. So if we do the dot product first, we get a -2, then we get 8, and then we get a -10. So we get our -4, which we had actually already calculated before. And then we divide by the lengths of each of those, and we get this, but that's the cosine of the angle, so you have to take the arc cosine of that to get approximately 1.7233 radians, and you could convert that to degrees. So the idea of two things being orthogonal in this class is basically equivalent to being perpendicular. It is a little bit more orthogonal is a little bit more general idea, but for this class you can think of the vectors being perpendicular, right, intersecting at 90 degrees or right angles. If the dot products are 0 of two vectors, then they are perpendicular. We will come back and use this time and time again in this class. So you can easily test to see if they're orthogonal through dot products. And you can make things orthogonal by making sure that the dot products, if you have some leeway, by changing values, you can make sure that they're orthogonal by making sure the dot products are 0. So are these orthogonal? Well, 1 times 1 is 1, 2 times 1 is 2, -5 times 1 is -5. We add those up, and we get a -3. That's not orthogonal. Yes, so that's 0 and 0. 0 times 2 is 0, 0 times 1 is 0. So yes, those are orthogonal. Here, you might say, well, you're not intersecting at 90 degrees. This doesn't have any length. It doesn't even have a length. And that's true, but we're going to stick with the definition here of we're going to say they're orthogonal if the dot product is 0. We're actually not going to say that they has to be some length. Here we get 5 and a -5, and we added those up to get 0. So those are orthogonal. It's a quick slide on how to write the Pythagorean theorem with the notation that we've used. I'm not going to spend much time on this. You can come back and look at this carefully. So this is another one of the big ideas in this section, really important techniques that we use. The big question is if we have two vectors, so the two vectors here are this green one that's u and this black one that's y. How do we find the point on, L is this line that is spanned by u. Like if we stretch u out and back, then we'd get this line. How do you find the point on this line, L, that is closest to y? And you might think this is just a geometry problem, it turns out that a lot of the important applications of linear algebra turn out to be projections, and they're projections, and the reason they're important is because you do approximations to reduce the complexity or reduce the amount of memory, like a lot of the compression things that happen. This is the basic geometry of what's happening with compression, with things like MPEG and other stuff. So they don't go through, in the book it does it a little bit. If you look carefully at pages 35 to 38 of the peanut butter book, I go through in pretty in depth and build up why you end up with this formula in a little bit more intuitive way than they do. So I'm not going to spend a lot of time here going through the details since I already do it there. But one thing to notice, so there's a couple things that throw students off, is this notation of the projection of, this is the projection of y on to u. So u is this vector, and y, we're projecting down. This is the idea of projection is like a shadow, right? Like if we have a light up here, okay, coming down, we're going to look at the shadow, or like a projection of a projector on the wall, that idea. So we have y that's coming on to u. This y here, that is the one that's being projected. The u is what we're projecting on to. You can think about y as a little higher than u, and you can think of it going down onto u, if that helps you out. And the other thing here, u's, all of the u's are, there's five vectors over here. 4 of them are u's. A projection onto u is a scaled version of u. Like wherever we end up with here, we're just going to be scaling up, or if you went all the way up to there, we're just going to be shrinking it back down so it's shorter. So a projection is a scaled version of the vector you're projecting onto, and this is just a number. This is a constant, because the dot products, you have each of the dot products is a constant. You have a constant divided by a constant, which is a constant. So you get that times a vector, and so you're just going to have a scaled version of the vector, which is what makes sense of what you get with the projection. So the y is only here once. It's in the numerator. Everything else is u's. And it's easy to remember the u, if you remember, we're projecting on to u, so the projection should be a scaled version of u. So if this is u and this is y, then the projection is going to be down here, and our new one's going to be out like that. That'll be our projection. This will be the projection of y onto u. So we're just scaling that one. This tells you how to scale it. U is the vector that you're scaling. So if you look at, you can make another vector. If you take y minus the projection, you get y minus, you get this vector here, and it's perpendicular to your projection. That's one of the key ideas here, and they walk through a proof here using the properties that we now know of the dot products. So we'll use this to construct things, orthogonal and perpendicular vectors, later on in the semester. And this might be the last slide. We're just doing an example here. Here we've got u, here we've got y. Let's write the vector, let's find the projection of y onto u. So we'll start off with the dot product of u and y in the numerator, and we'll do u dot u in the denominator, and we're going to multiply that by u. This is a scaled version, because we're trying to scale u so that it's the closest point to the end of y. One way to think about projections. And so this ends up being 7, this ends up being 46, multiply through there. And this is the projection of y onto u. So this is the scaled version of u. This is the piece that's perpendicular. So if we take y minus this projection, then we get another piece. And now what we've done is we've written y as a piece that's parallel to u and a piece that is orthogonal to u. So y, if that's y and this is u, we've scaled it up to u. We've scaled it up to get the closest point, and we've done that piece. So we've broken it down into two orthogonal pieces. And we'll kind of leave this for about half the semester, and then we'll come back to using this. It'll be important later on. We'll do projections a lot, but this idea of breaking it up, breaking a piece into two orthogonal pieces, breaking a vector into writing it as two orthogonal vectors, we'll come back to. Okay, thank you very much.